going to discuss briefly why we might want to use the Dirac notation and the operator and matrix approach to quantum mechanics rather than the more familiar and perhaps more intuitive position representation. So let's just think about an infinite square well as an example. So this is going to have a length L, and you can set this up with the well running from 0 to L or from minus L to L over 2. Now in the position representation we would write the eigenfunctions as something like phi n of x is equal to an sine n pi over Lx. If you had the well running from minus L to L over 2, you would have to include cosines as well. In operator or Dirac representation we would just write ket n. While you might argue this gives you less physical insight to the system, it is certainly more compact. The Hamiltonian is written as minus h bar squared over 2m d2 by dx squared in position representation, and in Dirac notation or operator notation is written as p squared over 2m. It is actually possible to represent the infinite square well in terms of ladder operators, raising and lowering operators, as we've discussed for the quantum harmonic oscillator, but it's rather complicated, so I'm not going to do that here, but it's just important to realize that. If we wanted to calculate a probability amplitude or a coefficient for a representation of a particular state of the system, then we would write an integral of, let's say, phi 1 star of x psi of x dx in position representation, where in Dirac notation we would write bra phi 1 ket psi. This of course relates to an expansion of a wave function psi of x. I'll just remove that little thing down here I didn't mean to put in, which we're going to represent as a sum over eigenstates Cn phi n of x. It's very similar in Dirac notation. You have ket psi is equal to sum over n of Cn n, where of course Cn is given by bra n ket psi, and in our position representation Cn is just the generalization of what we've already written, integral phi n star of x psi of x dx. Now that's a comparison, there's nothing particularly exciting about that. We can't really see why we're doing one or other of these choices. But now consider a system which is more complex, something where an analytic solution for phi is impossible. In that case, the operator representation becomes much better. And what we end up with doing is an abstraction. So we move away from position representation, we have matrices for operators, we have vectors for states, and also we can use an operator approach. This is what we did for the quantum harmonic oscillator. And the real value of the operator approach, where we have a plus and a minus, such that we write the Hamiltonian as h bar omega into a plus a minus plus a half, is that we can deduce the properties of the system without solving for the eigenvectors. So we saw, in fact, that you can, just from that form of the system, you can imply that the energy levels En are h bar omega n plus a half. More than that, you can calculate various matrices. For instance, you can calculate the expectation value of the position operator between two different basis states, and that leads to a matrix representation without explicitly calculating the eigenvectors. And so we can calculate, for instance, delta x squared, which gives us an estimate of the position error. because that's equal to the expectation value of x squared minus the expectation value of x all squared. We can calculate those with matrices without ever specifying what the eigenvector is. In systems where you might need the eigenvectors, of course, we can pass that over to a computational program. This extends to angular momentum, where you can deduce the properties of the z component of the system, and to spin, where there is no position representation. So in general, we see that it gives us a flexible approach to quantum mechanics, which allows really more power. It allows us to approach problems which we might not be able to do. And what we'll be looking at in the rest of the course is how we can create matrices, and then I can show you hopefully how you can use computational programs such as Python to diagonalize those matrices and deduce properties of the system without needing to do long complex derivations and solve differential equations.